time for us to see what could be so positive about something that has such a nasty name, route poisoning. Well, here's an example of a distance vector protocol walkthrough. And router 3 is connected to 10110/24, and it's advertising to routers 1 and 2 that that network is one hop away. Hops. Not a very scientific metric, but that's the only metric that distance vector protocols understand. It's called just a hop, and it's just like what it sounds. One router to another is one hop, to the next router, two hops, etc. So you can see another reason we might not use that. We'll revisit that later. But router 2 is getting that advertisement and sending it out another interface, and it's going to router 1. So router 1 at this point is hearing about 10110/24 from two different sources. And it's going to look at that and say, okay, that's the exact same route, but the metric is different. It seems to be faster if I go through router 3 as opposed through router 2. So we love this situation because we'll take all the redundancy we can get. If router 1 loses one path to 10110/24, it has another one. And we kind of like that. So, everything would be fine here, but until that route goes away. And I think you'll agree with me that when a route becomes unavailable, let's take another look at 10110/24. Let's say that network goes down. Well, when it becomes unavailable, we want all the routers to know about it and to know it as quickly as possible, right? I mean, it makes perfect sense. It's not a trick question. We want that convergence. We want them to know about it and say, hey, I don't know. Router 3 needs to tell them, hey, I don't know where this network is anymore. So what many people, including myself many years ago, thought is that router 3 would just stop advertising it. Well, there's a problem there because if router 3 simply stops advertising it, we're going to run into an issue, and I'm going to show you what it is here. And just as a quick reminder, what I'm showing you next is without route poisoning. And what would happen is that router 3 says, oh, okay, 10110/24 is unavailable. I'll stop advertising it. The problem is that doesn't do anything about the entry in router 2's routing table. So router 2 is just going to keep telling everybody, and in this case that includes router 1, hey, I know where 10110/24 is, and it's two hops away, even though the network itself is now unavailable. So it's not enough for router 3 to stop advertising it. It's got to have a way to tell everybody else, hey, that route just ain't around anymore. Because what happens next in our walkthrough without route poisoning is that router 3 is going to get an advertisement from router 1 and say, hey, that route is now available via router 1. I'll put it back in my routing table and start advertising it again. And what you end up with is this mess. Router 1 sends down an update to router 3 eventually, says, hey, I know where 10110 is. It's 3 hops away. And if that network is down on router 3, it's not going to be in the routing table. Router 3 looks at it and says, hey, okay, I'll just put that in my routing table and start advertising it. And 10110/24 is 4 hops away. So you can see, again, the trouble we end up with here. And this is how routing loops form if this were in the center of a larger network. So we end up with a real problem if we didn't have route poisoning. But fortunately, it's on by default. We do have it. So what happens in the case of route poisoning? Well, router 3 will continue to advertise the lost route, but it will do so with a poisoned metric. And this is another funny thing about RIP. Okay, RIP only understands hop count, and it understands that a hop count of 16 indicates an unreachable route. So that is the metric router 3 advertises with the route. So this is what we have in our network instead because route poisoning works. This is what happens. Router 3 doesn't stop advertising it. Router 3 continues to advertise it, but with a poisoned metric. That's where the name comes from. And it's telling routers 1 and 2, hey, it's 16 hops away. Well, routers 1 and 2 get that update and say, hey, I'm going to take that route out of my table and I'm going to stop advertising it. So as a result of that poisoned update, router 2 will no longer advertise the route up to router 1 or vice versa. So that's why route poisoning can be a force for good. It sounds evil, but it is indeed a force for good. Now let's go back and talk about that hop count for a second, because if this is the first time you've seen it, you might have just thought, that sounds pretty wacky. Well, neither version of RIP is very scientific when it comes to determining the metric of a network segment, because again, the hop count is the only thing it understands. Now you and I could look at a gig Ethernet link and a 56K link and say, I think the gig Ethernet link is a little bit faster. But the problem is RIP, or any distance vector protocol, considers these two links to be the same speed. It's one hop. It's the same metric to RIP. RIP can't differentiate. Now, you could go in and do some tweaking and make it understand, but we really don't want to be in that business because we have other protocols we'll learn about later that will see, okay, I see what's going on here with the speeds and I'll adjust. But distance vector protocols by default are not going to adjust. They're just going to use that hop count. Now, about that full routing update, every time, all the time is the way I used to remember it. Now, if your network is literally changing every minute, you should not be watching this video. You should be at work. And I kid, mostly. But again, we want a nice stable network. I'm sure we all have one. Little things happen from time to time or we wouldn't have jobs. But we do not need an update, especially a full routing update, every 30 seconds by default. Because these unnecessary routing updates, first they take up bandwidth, but first a router's got to put those updates together, got to send it, goes across the link, router on the other end gets it, has to unpack it, says, hey, it's like reading yesterday's newspaper. You already know everything, so you just throw it away. And so they're all thrown away, but at the same time, everything we do on a router or switch has a little bit of a cost. And we don't want that cost of having a full update every 30 seconds because you're looking at multiple packages, because it's not like if you have 200 RIP routes to advertise, they're not all going to fit in one packet. So you end up with multiple packets on top of that. I believe it's 25 per packet. So we're getting into some nuts and bolts there, but if you had that, it would be 8 RIP updates, 8 RIP update packets just to contain every route in that routing table. Not an efficient way to go about business, so we really don't like that. Now, EIGRP sends a routing update only when there's been an actual change to report. And even then, the update contains only the changes, not the entire EIGRP routing table. That's a pretty good enhancement. You see where that E is coming from now, right? That's just one of the enhancements. OSPF handles things a little bit differently, but take my word for it, it's much more efficient than distance vector protocols handle it. But before I'm accused of RIP version 2 shaming, version 2 was quite an improvement over version 1. And we know Cisco exams, really any exam, when you have 2 versions of something, you should know the differences between the two. And here are 4 that I think you should know. Version 2 supports subnet masking, variable length subnet masking, if you will, VLSM. More on that topic coming in the next section. For now, just remember version 2 supports it, version 1 does not. Version 2 multicasts its updates. And this is a good IP address to memorize, frankly. 224.0.0.9. I'm going to show you so many debugs in the next couple of labs that that address will be, you'll see it when you close your eyes, go to sleep at night. It's a lot more efficient for a routing protocol to multicast than to broadcast to 255 for each octet. But that's what version 1 does. It broadcasts, where version 2 multicasts its updates. As I mentioned previously, just a quick reminder, version 2 offers update authentication, version 1 does not. And version 2 allows the network administrator to configure route summarization manually. Version 1 doesn't allow that, and we will see in a lab why that can be so very important. Speaking of labs, this is where we're going to start with RIP, and it should look awfully familiar. We've got our 172.12.123.0/24 network running on our serial interfaces on all 3 routers. Our service provider cloud or frame relay cloud, we're not configuring that because that's our service provider. And we have a loopback interface on routers 2 and 3. There isn't one on 1 yet. And I would go ahead and write this out because, again, we're not going to continually come back to the screen and look at the drawing. And I've got a couple of different configs for you, a couple of different labs, and we will be subtracting and adding loopback interfaces, but that serial cloud, the serial connections will always be there, unless I tell you otherwise, of course. So go ahead and jot this down, take a break, and when I see you at the beginning of the next video, we will jump straight into a RIP config. See you there.